analyze the frame shown in figure by matrix stiffness method. So this is a frame oriented problem. It will go like this: first beam oriented problem and the frame oriented problem, and the next type will be wave oriented problem. Okay. Now for this structure, you have joint A, B and C. So these three joints are beam oriented joints and joint D is a column joint. And the joint A is being hinged and joint B is known as partially hinged. Joint C and D are fixed. Now you know that the difference between hinged joint and partially hinged is, hinged joint you will be having purely zero moment, and at partially hinged joint you will be having summation of all moments will be 0. In this problem you will be getting 3 number of moments at joint B, that is B to A, B to C and B to D. So these are the 3 members are connected to joint B. Here after finding the answer, if you add all 3 moments you will be getting 0 at the joint B. So this is known as partially hinged. Okay. And now the EI is not given separately and you can take it as a constant. Here what you have to do is analyze the frame shown in figure by matrix stiffness method. So you have a 2-point load and in column you are not having any load. First step is to find kinematic indeterminacy, that is Ki. So how to find that? Number of joints into 3. So how many number of joints are here? 1, 2, 3 and 4. 4 number of joints, so 4 into 3 will be 12. So 12 minus number of support reaction. So you have 2 and you have another 2 support here. It is 4, and at fixed joint you will be having 3 number of support reaction, and fixed joint D you have 3. So 3 plus 3 is 6, 6 plus 4 is 10. So 12 minus 10 will be 2. So this will be the kinematic indeterminacy. Okay. So what do you mean by that? Is one which is there at joint A and another one at joint B. So these are the 2 possible kinematic indeterminacies. So rest of the portion you will be not having any movement of a joint. Okay. So next step is, step 2 is finding fixed end moment. Consider AB as fixed. At the center span you have the load 60 kilonewton. You have 2 meter and 2 meter which are equal in length, and you can use WL by 8 as the formula. So W is 60 and length is 4 meter divided by 8. So if you have a fixed beam carrying a point load at center, you can use WL by 8. Your answer will be 30 kilonewton meter, and for BA you will be getting the same answer. And if you have a point load not acting at the center, you have WAB square by L square, where A is 4 meter and B is 2 meter, W is 120. So if you divide by L square, so L is 6, you will be getting MFBC as minus 53.33 and 106.67. So this is B to C and C to B. Whereas in case of B to D, you don't have any load, hence there will be no movement. Now in case of fixed beam, you have found that there is no fixed moment are there, but after analysis you will be finding there is distribution of moment after analyzing. So even though you found that the fixed end moments are there for B and C only, so B and D is not taking any load. This is the initial assumption. But when you process this matrix stiffness method, you will come to know that there are some distribution of the moment between this D, B to D. Why? Because the B joint carries 3 number of members and there will be distribution between these three members according to the stiffness component. So due to this, you will be having a slight moment which is being transferred from BA and BC. So these two moments will be transferred to D, and finally you will be getting some moment at the member B and D. Okay, let us do that. And step 3 is finding transformation matrix, that is beta. You know that this is the frame, remove all the loads, and here are the kinematic indeterminacy number 1 and number 2. So you found two number of kinematic indeterminacy, and here are they. Now how to find beta matrix? Apply a unit moment 1 at the Ki1. So this is the first kinematic indeterminacy. So assume this as 1 and rest of the component will be 0. So this is the element coordinate. For better understanding, since you have 3 number of element, you will be having 6 number of nodes. Okay, by this understanding, if you apply one moment at the node 1, rest of the nodes will be having 0, and this will be your beta matrix 1. You have 1, 0, 0, 0, 0, 0, 5 number of zeros. So you have applied 1, 1, 2, 3, 4, 5. So rest of the all the nodes will be 0 here. Now you apply a unit moment at the joint B. So how many members are connected with joint B? That is the node 2, 3 and 5. So these 3 nodes will be having 1 and rest of the nodes will be having 0. Okay. Now if you write the transformation matrix, node 1 is 0, node 2 and 3 is 1 and 1, and node 4 is 0, node 5 is 1 and node 6 is 0. This is the way to take transformation matrix. So how many members are connected with this joint? Will be having unit moment. Okay, now you got two number of beta matrix. Since you have Ki as 2, you will be getting two number of beta matrix. So it is compiled here, and you got 1, 5 zeros and 0, 1, 1, 0, 1, 0 as your answer. 2, 3, 4. Step number 4, and forces in element coordinates, that is P naught. So that is fixed and moments. So what are your answer? Minus 30, plus 30, and you got for the span B to C minus 53.33 and 106.67. So these two are the moments. So at the column end you don't have any moment, hence P naught is this answer. And if you find F naught equal to B transpose P naught, so beta transpose, you know that these are the values. Now you have changed the column into rows, and P naught is, you have found out the P naught, minus 30 plus 30, minus 53 and 106. So these are your answers. Now you have to multiply the first row into the column. So you will be getting 1 into minus 30 as minus 30, rest of the component is 0, hence you will be not having any answer, and you got minus 30 here. And now if you multiply the second row into this column, first factor will be 0, and 1 into 30 will be 30, 1 into minus 53.33 will be minus 53.33. So you will be getting 30 minus 53 will be 23, and next factor will be 0, and last factor will be, last remaining two factors will be 0. So you will be getting minus 23.33. This is your F naught. And how to find the F of F, which is the formula? You know that there are no joint force. So there is no load which is acting at the joint. So this joint, and or in all the joints you are not having any load, hence F of F will be 0. That is, then F of F minus F naught is, so you know the F naught value which you have currently found here. So F of F is 0, hence you will be getting minus of the value. So whatever you have, both values are minus here. So minus and minus will get cancelled and 30, 23.33 will be getting here. Okay. Now you got small k as element stiffness matrix. How to find k? You have three number of elements, that is AB, BC and BD. So three elements, you have to write three number of element stiffness matrix. So K1, K2, K3. These are all small k. Okay. Now if you write that, what is the formula? The formula is EI by L 4224. So EI by L, so first length is 4 meter and hence it is divided for all the components. 4224 is the formula. You have divided by 4 for all the components. So for the second member, the length is 6 meter, hence you have divided all the parameters by 6. Your conventional value is 4224 for all the parameters, and for the third span B and D it is 3 meter. You have divided. Now after dividing you will be getting the small k, that is element stiffness matrix. So this is your answer with the common factor of EI. Okay. Now how to find system stiffness matrix? That is capital K is beta transpose K into beta. Now beta transpose is the two values and the K matrix is here, also the beta. Now if you multiply first row into this first column, you will be getting 1. So 1 into 1 is 1 here and remaining components will be 0, and first row into second column you have only first parameter, hence 1 into 0.5 will be 0.5. The next parameters will be 0. Why? Because you have the component of 0 here. Now the second row into this column, so you have the column 2 and 3, so 2 is active here, so 1 into 0.5 will be 0.5. Next, for this row into the second column, 1 into 1 is 1, remaining components will be 0. For row into this third column, you will be getting 1 into 0.67, you will be getting 0.67. Similarly, if you multiply row into this column, you will be getting this answer. Okay, now after getting this, you have to multiply with this component, that is beta. Now if you multiply 1 into 1 is 1 and 1 into this second component. So you are having second parameter which is 0.5 into 1, which is 0.5. Now the second row into the second column, you will be getting 0.5 into 1 is 0.5, and this second row into the second column, 1 into 1 is 1, 0.67 into 1 is 0.67, so totally 1.67. So plus this component will be 0 and 1.33 into 1 is 1.33. So totally 1.67 plus 1.33 is 3. So you got the value of 3 here. So after multiplying, you will be getting capital K, that is system stiffness matrix, as 1, 0.5, 0.5 and 3. Now how to find the inverse? So which I have discussed in last class. First you have to find the determinant. What is determinant? Multiply this diagonal 1 into 3, that is minus 0.5 into 0.5. So what is the determinant value? This is 2.75. Now inverse of the 2 by 2 matrix is 1 by determinant of the matrix. So what is the determinant, which is 2.75, and 1 by 2.75 into, now you have to interchange the value, that is 3 is gone here and 1 will come here, and the next diagonal will be 0.5 and 0.5, which will be in terms of minus. You have to change the sign. Okay. Now next step is system displacement vector. How to find that? Small u equal to K inverse f of f minus f naught. So what is K inverse? You have currently found here, and f of f naught you have found out as 30, 23.3. Now if you multiply the component 3 into 30, 0.5 into 23.3, which will be getting one answer, that is 28.49, and minus 0.5 into 30, 1 into 23. If you add that, you will be getting 3.02. Now this is your u. Now multiply this u value by beta matrix. This will yield you element displacement matrix. 1 into 28, which will be 28, and 1 into 3.02, next column, next row into this column will be 1 into 3.02, and this will become 0, 1 into 3.02, and finally 0 into 0 is 0. Yes. Now, next value is P dash. How to find that? K matrix into del. So, this is your element stiffness K matrix, and del you have currently found at the last step. So, you multiply each row into this column. The formula is always rows into column. So, row is 1 into 28.49, 0.5 into 3.02. Now, this will yield you this answer, which is 30. If you add this, you will be getting, that is half of 3.02 plus 28.49 will give you 30. Likewise, you multiply row into this column, you will be getting this P dash. Now, how you can find P naught? P naught you have already found out, that is the fixed end moment. So, these are the fixed end moment. Now, by using P dash and P naught, you can add that. So, if you add all the components, plus 30 and minus 30 will become 0, and if you add that, you will be getting 47.27. Like that, if you add that, you will be getting PF, so which is your final force. And you can find the positive bending moment, that is WL by 4 and WAB by L. So, this is your simply supported beam case. So, you got the positive moment by considering this as the simply supported beam. So, B to C is also simply supported. The formula is WL by 4, which will give you 60, and B to C is this WAB by L. And 120 into A is 4 meter and B is 2 meter divided by L is 6 meter. So, which will yield you the 160 value. Yes. At joint A it is 0, at joint B you got the value which is 51 and 47 and 51, and at joint C it is 107, joint D it is 4.02, that is B to D, and D to B is 2.02. Now, this is what I highlighted earlier. When you find the moment, there will be distribution of the moment between this joint. So, from the joint B, you will be having moment distribution, and you can find 4.02 as the distributed moment and 2.02.